Okay, next we're going to talk about probably one of the most important concepts of the link layer is basically access links and access protocols and how we access multiple link types, which is part of, you know, one of the things that the link layer has to deal with. So basically there are two types of links that we're going to address, point-to-point and broadcast. So point-to-point is used off, like, for example, an example of a point-to-point link would be dial-up access. And also if you're connected up to um, an Ethernet switch, basically you have one cable from your host going right to the switch. That would be a point-to-point type of link. A broadcast um, link would be an example of the old-fashioned Ethernet that used to have was bus-based, which had a coax cable, and you basically had your connector basically connected your end station into the coax bus. Upstream HFC, which is used by the cable providers, um, is the situation where you have a broadcast-based link. We really haven't covered. I kind of skipped over that. We may cover that in our later lectures to talk a little bit about how the cable system provides Ethernet access, but not going to be part of the review. And also, wireless networking works on a broadcast basis as well. So a multiple access protocol is used when you have a single shared broadcast channel. So this was a big issue with the old-fashioned Ethernet, less so for modern wired Ethernet, but it's also an issue for wireless. So it's an important concept. So if you have a shared broadcast channel, you have to deal with the problem of a collision where you have, two nodes transmitting simultaneously. Um, they're both going to put the signal in the wire at the same time, so you have to have some sort of way to deal with collisions. So because of that, you have to have at the link layer some sort of multiple access protocol. And basically what you're going to do is have some sort of mathematical algorithm that's going to determine when different nodes can transmit and when different nodes can wait. Now there's a lot of different um, over the course of history. There's been different types of multiple access protocols, but we're going to basically um, just really focus, minimize our focus, and not cover everything. We're going to cover basically what I feel is just the most important for this review. So you basically have to have an algorithm that determines how the channels are going to be shared, and there's no ability to have any out-of-bound coordination. So you're going to use up some available bandwidth coordinating the multiple access protocol itself. So you're going to have some trade-offs in what you end up choosing for a multiple access protocol as a result. So an ideal multiple access protocol would be one where you imagine you have a broadcast channel that has this maximum rate of R bits per second. So in a perfect world, when a node wants to transmit, it can send at a rate of R when one node can transmit. When M nodes want to transmit, they can send an average rate of R over M. That means all transmitters get an equal share of the available bandwidth. This broadcast channel would this ideal multiple access protocol would be very very efficient. It would be fully decentralized. It wouldn't have to have a special node to coordinate transmissions that might fail. There's no synchronization of clocks or slots, which add overhead and decrease overall reliability if there's a clock synchronization problem, and is overall very simple. Of course, a simple protocol is an efficient protocol. So we're going to talk about three broad classes of multiple access protocols. So you basically have the concept of channel partitioning, random access, and taking turns. So let's talk about those individually. So in the first class, in channel partitioning, we basically divide the channel into smaller pieces, either using time, frequency, or code distribution. So we either separate it by different time slots, or we divide the channel up into frequencies, or we use some code to differentiate the different uses of the channel. The advantage of this is there's less processing overhead because you basically just have your time slot and that's pretty much it. There's not much for decision making. There's no risk of collisions. The problem here is that you never maximize the use of the broadcast medium because you can't have, if no one else is broadcast, no one else is using the medium, you still have your small channel. Random access works really well if you're the only person broadcasting. It could work very poorly if local broadcasting simultaneously because you basically have to allow collisions and then have some way to recover from the collisions. And then finally you have the concept of taking turns, like with a token, where node takes a turn, and nodes of mortise send can take longer, but there's issues here as far as reliability. What if a node doesn't get has a problem and doesn't give the next node a turn? So those are the basics, and we're going to talk about these in a little bit more detail. Okay, we're going to talk a little about time division multiple access or time division multiplexing. And basically what we're going to do is we set the channel up so every user gets a time slot. So each station, each node gets a fixed slot in each round. The problem here, of course, is unused slots go idle, so that's one of the disadvantages. So you have a round of basically 6 slots, and you have, in this particular example, so you go kind of round robin, everybody gets a turn. And in this case, you have hosts 1, 3, and 4 have packets, but you basically have all this, basically half of the available bandwidth is basically unused. In frequency division multiple access, you basically separate the channel into different frequency bands. So basically, you have different frequencies. So this particular channel, the signal sent with this frequency and sent with this frequency and this frequency. So you can see the frequencies get higher over time, and basically you just knowing the frequency, you can basically remove the signal at the other end. So we basically have the same problem as time division multiple access, where the unused frequencies go idle. So it's kind of the same idea, just using frequencies instead of time slots to share the channel. Another situation rather than separating the channel, is to have a random access protocol that assumes the possibility of collisions is going to happen. So we're going to try to maximize usage, but we're going to increase our risk of collisions. So when taking a look at random access protocols, like I said, the advantage of the random access protocol is that when a node has a packet to send, the node can transmit at the full channel data rate of R. And there's no a priori coordination among nodes. Unlike in previously where you had to share time or frequency, there's no coordination prior to sending a packet. However, the downside of random access protocols is you have the possibility of a collision where you can have two nodes sending data, which means basically sending a signal on a wire that's going to basically collide. So each random access protocol has to figure out how to detect a collision and how to recover from a collision. So basically it usually means you have to retransmit. So there are different examples of random access MAC protocols, and the one that we're going to focus on is the one that actually has been used in the past. It still exists, but it's not really used that much anymore, which is CSMA-CD. We are going to cover CSMA-CA later on in this class, but not in this particular lecture. So let's move along. Let's talk about what CSMA means. So that's basically carrier sense multiple access. So basically what we're doing here is we listen before we transmit. If we sense that the channel is idle, then we go and transmit that the entire frame. If we realize the channel is busy, we defer our transmission. Obviously, there's always a possibility that two nodes are going to listen and transmit at the same time, so we can't solve that problem, but at least we don't try to transmit once if the transmission medium is actually being used. And basically to kind of relate this to a human analogy, if you're at a dinner party, it's kind of a very natural thing. A bunch of people are talking, you listen to other people until there's some silence, and then you talk. And that's kind of what the computers are doing in CSMA. So I'm going to switch slideshow on this particular slide. Okay, so like I said, in this case, collisions can still occur, and part of the reason is the fact that even though you have two nodes that listen, they don't hear anything on the wire. The problem is there could be some sort of propagation delay between the time when there may be something on the wire, but that noise on the wire hasn't reached that particular host. So, and this is basically trying to be an example of a particular time T0, a particular time T1, where it takes time for there to be to detect the noise, and the time when that overlaps, and then there's times when it looks like basically you have silence, but you really don't. So, like I said, the downside of this type of situation is that you're going to basically waste a packet every time there's a collision. So yeah, because you're going to have to rebroadcast. So, like I said, it's very possible due to the distance between nodes and just the time it takes for a signal to travel along the wire. If the distance is longer, if distance between the nodes are longer, and it takes longer for the, that's going to obviously mean it's also going to take longer for the signal to traverse the wire. So if you have one node here and one node there, trying to send something simultaneously or try to listen, and something else on the wire, they may not hear it. So this guy sends something, this guy might not hear it yet, and he decides to send something. And that's why when you use something like CSMA, there's usually a limit on how long you're going to let these links be. And that's due to, if it's too long, you're going to have too many collisions. So we add to our carrier sense multiple access collision detection. So what we do here to try to reduce that time wasted of sending a packet that's going to have to be retransmitted because the medium was being shared, we basically detect when a collision does occur, and we quickly abort our transmission so we don't waste the channel. So that's a little bit more efficient. So basically, collision detection is very easy to do in a wired LAN. Basically, you measure the signal strength and compare the transmitted and received signals. So if the signal strength is higher, that means there's another signal on the wire. So you have a collision. This is a little hard to do in wireless LAN, so when we get to the discussion of wireless LANs, we're going to describe what we're going to use instead of CSMA CD. And this is basically, the human analogy is a polite conversationalist, so you have somebody that's having a conversation and they if they detect someone wants to talk, they don't interrupt them, they say, you go ahead. And that's kind of what's happening here. So in IEEE 802.3 defines the CSMA CD that's used for Ethernet. So basically, if you hear that the medium is idle, you transmit. If you detect that it's busy, you wait until it's idle and then you transmit immediately. Obviously, you can't eliminate the possibility of a collision, so basically you have to deal with it. So basically the specification says for the first thing you do is you transmit a jam signal for one slot, which is 51.2 microseconds. This is basically linked to the largest allowable link in the IEEE 802.3 spec, so that's the time it takes for the jam signal to traverse across the whole wire. And so the purpose of this is to let everybody know that there was a collision. Then you wait for a random time up to 16 times, and the random time uses what's called truncated binary backoff. We're going to go get to that in a little bit. The collisions are detected by monitoring the voltage. Like I said, if the voltage level is higher than the voltage level you would transmit at, then you know there's a collision. And like I said, the length of the cable is limited to 2 kilometers, and that's how long it takes, the 51.2 microseconds, for the signal to traverse fully across the 2 kilometer length. So let's talk in a little more detail of how the CSMA CD algorithm works. So kind of step through this, so we're going to go through a state diagram. Okay, so in the first step in the Ethernet CSMA CD algorithm, the NIC card receives a datagram from the network layer, some sort of IP datagram and then it creates a frame. If the NIC senses the channel is idle, it starts the frame transmission. If it senses it's busy, it waits until it detects that the channel is idle, then retransmits. And like I said, it's basically monitoring the voltage levels on the channel. If the NIC transmits the entire frame without detecting another transmission, it's basically done with the frame, and it can basically go back up to step 1. If the NIC detects another transmission while transmitting, it aborts and then sends the jam signal. After aborting, the NIC enters a binary back off, and keep in mind that all of the other NIC cards that may be transmitting simultaneously are doing the same thing. It basically chooses a random number k, arranged from 0 to 2 to the m minus 1, where m relates to the number of collisions, so that number k gets larger, that range gets larger the more collisions that you have. And then, based on that number, it weights k to the 5 times 12 bit times, and then it returns to step 2. And as you've noticed, that this back-off interval gets longer the larger that the number m gets, and m, of course, is related to the number of collisions. So here is basically how this works. So we start off, we set our counter to 0, and we go to a decision. Is a medium idle? No, we wait 1 time slot, and we check again. Once the medium is idle, we send out transmission. Is there a collision during transmission? If it's no, then we're all done. If it's yes, then we set the counter. We increment the counter. Is the counter greater than 16? And then if not, we say no. Then we're going to wait some back off period. Then go back and listen to for idle. We make that decision again. And if we have collisions, we will run through this loop 16 times. If it gets greater than 16, then we just say, forget about it, we're going to abort. And then usually some sort of error message is going to get sent back up the protocol stack, basically saying that we weren't able to send. And it's up to the application to resend at that point.